The largest magma chamber ever discovered beneath the Earth's surface lies beneath the Yellowstone supervolcano, and new research says it might be even bigger than we thought, maybe twice as big as we thought. But why do scientists care so much about the size of this magma chamber? What does it mean for the future of Yellowstone? And could this change how we think about the future of our planet? Hello, and welcome to my channel. Today, we are off to Yellowstone National Park to talk about a recent paper published by the PANGAEA journal. The paper is titled Insights into the Origin and Evolution of Yellowstone's Giant Magma Chamber from First Principles Modeling. Now let's talk about what all that means. Yellowstone is the site of the largest active volcano in the contiguous United States. It has had 3 major eruptions in the past that have left massive deposits of ash over large portions of North America. If you visited Yellowstone, you may have seen some of these vast layers of ash exposed along the walls of the Grand Canyon of the Yellowstone or in the cliffs along the river as you drive between Old Faithful and the Grand Canyon. These ancient eruptions at Yellowstone created the vast majority of the park's iconic geyser basins and hot springs, as well as the beautiful but deadly supervolcano that lies beneath. The magma chamber beneath Yellowstone is thought to be the source of all of these features. The magma chamber is a vast underground pool of molten rock and crystals called magma, which comes from the Latin word for to know or to be able to. Scientists sometimes call this magma a magma ocean because of its thick, gooey, liquidy consistency. Just like the ocean, this underground sea of magma extends deep below the Earth's surface, but unlike the ocean, where sunlight can penetrate hundreds of feet below the surface, the magma ocean beneath Yellowstone lies deep below the surface where no light can reach. Because of this darkness, scientists have relied on other tools to learn about the magma chamber, such as measuring the small earthquakes that happen around the Yellowstone supervolcano. Using computer models of how waves move through the Earth, they can then infer the physical properties of the rocks below the surface, like whether they are solid or liquid. In 2015, researchers reported evidence of this giant magma chamber, roughly 43 by 56 miles across and extending nearly 30 miles deep below the surface. This is equivalent to the entire state of Connecticut fitting inside with room to spare. If you were standing at the top of the magma chamber, you would be standing about 6 miles above the molten rock. That's higher than Mount Everest, the tallest mountain on Earth. Since this discovery, scientists have been working to understand just how the magma chamber formed and if there are other chambers connected to the Yellowstone supervolcano. The new study used a computer model to better understand the evolution of the magma chamber over time. The model simulates how magma moves through the Earth's crust and how it interacts with the surrounding rocks. By simulating how this magma interacts with the crust, the researchers hope to determine what the magma chamber might look like today, and if it has changed shape or size since its formation. To make the model, the team made several assumptions about the composition of the magma and the rocks surrounding it. They also looked at previous studies and data collected at Yellowstone to help calibrate their model and ensure that it was accurate. Then they ran the model millions of times to simulate different scenarios and see which ones best fit the data they were looking at. So why do scientists care so much about the exact size and shape of the magma chamber? Well, it turns out that the magma chamber's shape and size will affect how well magma can move through the Earth's crust. As the magma chamber grows, the pressure inside of it increases. When the pressure gets high enough, the magma can push its way up through the surrounding rocks, which can lead to an eruption. However, not all magma chambers erupt once they reach a certain pressure. The shape of the magma chamber can help scientists better understand why or why not it erupts. A magma chamber that is tall and thin may be more likely to erupt than one that is wide and flat. The computer models that scientists use can help them predict how magma chambers might behave in different scenarios. In theory, this could help them better understand when a volcanic eruption might happen. After running all those simulations, it looks like the magma chamber at Yellowstone might be larger than we thought. It could be twice as big as the chamber we identified back in 2015. The The new research suggests that the chamber is closer to 75 by 93 miles across and extends down 43 miles below the surface. That's about as wide as 24 American football fields lined up side by side, and almost as tall as 43 American football fields stacked on top of each other. All of that magma adds up to about 800 cubic miles worth, which is enough to fill up 322,000 Olympic-sized swimming pools. The model also suggests that the magma chamber has been slowly growing over time, and that it may continue to grow in the future. As the magma chamber grows, the pressure inside of it will increase, which could eventually lead to an eruption. However, the model does not suggest that an eruption is imminent. It's still unknown exactly how long it will take before the pressure builds up enough to cause an eruption. Based on previous eruptions at Yellowstone, scientists estimate that the next eruption will probably not happen for another 10,000 years. So don't worry. You should be safe visiting Old Faithful whenever you want. But seriously though, scientists don't actually know how big this magma chamber is, or if it will erupt anytime soon. This is just a model, and models are only as good as the data that goes into them. Unfortunately, there is only so much data available from Yellowstone, and scientists have to make assumptions based on what data they do have. For example, one assumption they had to make was the viscosity of the magma. Viscosity is a measure of how thick or runny a liquid is. Runny honey has a low viscosity, while peanut butter has a high viscosity. Scientists know that the magma beneath Yellowstone is probably pretty thick and sticky, but they don't know exactly how thick, so they had to assume a certain viscosity for the magma in order to run the model. Another assumption they had to make was the geometry of the magma chamber. Is it perfectly circular? Is it shaped like a rectangle? Does it have any weird protrusions or indentations? Scientists don't know exactly what the magma chamber looks like, so they had to make an educated guess. Based on these assumptions and the available data, the researchers were able to build a model that seems to fit the available data pretty well. But it is possible that the true size and shape of the magma chamber are different from what the model predicts. It is also possible that the magma chamber has changed in size and shape over time in ways that the model does not account for. That being said, the model does a pretty good job of explaining some of the features at Yellowstone. For example, it can explain why there are so many geysers and hot springs in the park. As the magma chamber heats up the surrounding rocks, it creates hot water reservoirs. This hot water is less dense than the cooler water that is deeper underground, so it rises up toward the surface. As it rises, it creates geysers and hot springs. The model can also explain why the magma chamber is not perfectly circular. The surrounding rocks are not perfectly uniform, so the magma chamber has been deformed in some places and may be growing faster in others. This is why it is so important to continue collecting data at Yellowstone and other volcanoes. With more data, scientists can improve their models and better understand the risks posed by these volcanoes. Better understanding the magma chambers beneath volcanoes like Yellowstone is crucial for predicting when they will erupt. This is not only important for the people who live near the volcanoes, but also for the entire planet. Large volcanic eruptions can inject huge amounts of ash and gases into the atmosphere, which can block sunlight and cause global cooling. For example, the 1815 eruption of Mount Tambora in Indonesia is thought to have caused the year without summer in 1816. During that year, the Northern Hemisphere experienced unusually cold temperatures, which led to widespread crop failures and famine. Volcanoes can also release large amounts of carbon dioxide and other greenhouse gases, which contribute to global warming. For example, the 1980 eruption of Mount St. Helens in Washington state released about 1.6 billion pounds of carbon dioxide. That's equivalent to the annual emissions of about 320,000 cars. While volcanoes are a natural and important part of the Earth system, they can pose a serious threat to life on Earth. Understanding how magma chambers work will help us better understand and predict volcanic eruptions, which could save lives and prevent major disruptions to the global climate system. If you enjoyed this episode, please subscribe to my channel and check out my podcast.